Hello, welcome to the 19th class of this course. In the last two classes, I talked about Bessel function of first kind and Bessel function of second kind, which are basically the Newman functions. In this class, I will talk about the graphs and zeros of Bessel functions. So let's look at the Bessel function of first kind at first. This is the Bessel function of first kind, and if you can see, for example, if you look at the z0x, for example, in that case you can see that it is written as sum over r equals to 0 to infinity minus 1 whole to the power r divided by gamma of r plus 1 times gamma of r plus 1, because I am putting n equals to 0 here, times x by 2 whole to the power 2r. Okay, so I have put n equals to 0. And now if you look at the first term of this z0x, that means if you look at the first term of the summation, that means when you put r equals to 0, so then this minus 1 whole to the power r, it is basically 1. This gamma of, it will be gamma of r plus 1, which will be just gamma of 1, that is again 0 factorial, which is 1, and this x by 2 whole to the power 0, that means it's 1. So the first term, or rather the n equals to 0th term, that is 1, and then there will be other terms for r equals to 1 to infinity. So for all the other terms in the summation except this r equals to 0th term, there will be x multiplied with it. And now if we put x equals to 0, in that case we will see that this z0 at x equals to 0 is nothing but 1. So if we plot z0, it will start from 1 and it will oscillate like a damped cosine. So here I plotted this j0x, this is jnx for n equals to 0, so this is j0x, this blue curve, and it's acting like a damped cosine function. Similarly, if you look at this j1x, so here I have I wrote this j1x, and if I write this 0th term in the summation, then you will see there will be x by 2 present here, because of this 2r plus 1, there will be x by 2, and in all these terms there will be x multiplied with it. So what I am trying to say is, for j1x, in all these terms of the summation there will be x multiplied with it, or x or some higher powers of x. So in that case, at x equals to 0, this j1x will be 0, and similarly for all other, like j1x, j2x, j3x, j4x, all of these Bessel functions, it will start from 0. At x equals to 0, it will be 0, because of this x or higher powers of x multiplied in the summation terms. So here I plotted this Bessel function of first kind for n equals to 1. So this is the j1x, and this is how it looks like. So it looks like a damped sine wave, but it's not actually a damped sine wave, that I will discuss later. So you can see that its amplitude is gradually decreasing, and it's starting from 0 at x equals to 0. Similarly, I have plotted the other Bessel functions also, Bessel function of first kind. This blue one is j0x, that we already discussed, and this red one is j1x, here you can see in the legend, and this yellow one is j2x, this other one is j3x, this violet one, and this green one is j4x. So this is how they looks like. So except j0x, which starts from 1 at x equals to 0, all the other functions, all the other Bessel functions of first kind, j1x, j2x, j3x, j4x, they are starting from 0 at x equals to 0. So all these j1x, j2x, j3x, they behaves like a damped sine wave, whereas this j0x, it behaves like a damped cosine wave. Now let's talk about the zeros of this Bessel function. The zeros of Bessel function means the values of x, in this case this alpha 1, alpha 2, alpha 3, alpha 4 and alpha 5, where this Bessel function becomes 0. These are called the zeros of Bessel function. So for example, you can see at x equals to 2.4, around, near about this, at x equals to 2.4, this j0x, it becomes 0. This is the first 0 of this j0x. Similarly, another 0 is around 5.52, that we are calling the alpha 2, and the other 0 is around 8.65 and all. So these are called the zeros of this Bessel function. And here I have make a chart of zeros of Bessel functions, a few zeros of Bessel functions for j0x, j1x, j2x, j3x and j4x. So for j1x, j2x, j3x and j4x, at x equals to 0 is already a 0 of this Bessel of this j1x, j2x and j3x, j4x. But rather than that, these are the values of x where this j1x or j2x or j3x will be 0. Now if you notice, why I am calling it that this j0x looks like a damped cosine wave, but it is not exactly a damped cosine wave. It's because if you can look at this difference between those zeros, you can see it's not a regular pattern, it's not a regular interval. If it's a damped sine wave or if it's a damped cosine wave, then the frequency will be same in all those intervals. But here this difference between these zeros, they are changing. So these are not exactly damped cosine wave. Similarly, this Bessel function of second kind, it is defined like this, and if I plot it, this here it's a plot of y0, y1, y2, y3 and y4x, and you can see that at x tending to 0, all these Bessel functions of second kind, it going towards infinity, so it is diverging. So it basically says that the integer values of p, the ypx, these are really independent of jpx, because at x tending to 0, those were finite. The jpx, those are finite, that we saw in the plot. So this is how the Bessel function of second kind looks like. So I will not show again the zeros of this Bessel function of second kind. So these are the plots, these are the graphs of this Bessel function of first kind and second kind. In the next class, I will talk about the generating function of Bessel functions, and I have attached assignments in the description section, which covers basically the Bessel function of first and second kind. Please do them, you will get a better idea of this Bessel function. So that's all for today. Bye.